Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on a case study in which petroleum contaminants from a UST were reduced to non-detect within 60 days using PetroFix. With that, I'd like to introduce our presenters for today. We are pleased to have with us today Gordon Dean, Vice President of Advanced Environmental Technologies. Gordon provides senior engineering support for remedial actions and consulting services for clients purchasing environmentally distressed properties nationwide. He is a professional engineer in multiple states with more than 37 years of experience in the assessment and remediation of hazardous waste and petroleum contaminated sites, and has been responsible for procurement and management of more than $750 million in total contracts. We're also pleased to have with us today Chad Northington, Southeast District Technical Manager for REGENESIS. Chad is a professional engineer with almost 20 years of experience in the environmental field, in the areas of site investigation, remediation system engineering and construction, project management, and technical assistance. In his current role at REGENESIS, he works directly with environmental engineering and consulting firms to develop successful remedial approaches for their clients by offering design, application, and performance review services for in-situ applied groundwater and soil remedial strategies across a broad spectrum of technology classes. We're also pleased to have with us today Todd Herrington, Global PetroFix Product Manager for REGENESIS. Todd collaborates with the sales, operations, and R&D departments at REGENESIS in order to provide successful solutions to REGENESIS clients using PetroFix Remediation Fluid to treat sites impacted by petroleum hydrocarbon contaminants in soil and groundwater. He has over 20 years of environmental remediation experience and has been with REGENESIS since 2004. All right, that concludes our introduction. So now I will hand things over to Gordon Dean to get us started.
Thank you, Dane. Pleasure to be here today. I'll be talking about a case study. It was the first field use of PetroFix. So we'll start with, for those of you that aren't familiar with it, PetroFix is a proprietary technology produced by REGENESIS. It's a microscale activated carbon-based remedial fluid. They take 1 to 2 micron size carbon particles suspended in an aqueous solution, and it's for those of you that are familiar with FlumeStop, it's a somewhat sister technology to that, but it's designed for source areas and higher contaminant concentration, so it can treat up to 100+ milligrams per liter of total contaminants. Cannot do free product, but it really opens up a wide range of sites to remediation. And that's not also to say that it won't do polishing steps too. It'll do basically 100 milligrams down. So a very wide range of applications. They have also included the electron acceptors to enhance biodegradation. As opposed to some other technologies, you don't have to do separate injections of oxygenates or electron acceptors, that kind of thing. And Chad's going to talk about that a little more in detail later. Now, the pilot test site was the Reef Deli site in Panama City Beach, Florida. It was the first field use of PetroFix outside of the laboratory. It's an insurance site that we have, so it's privately funded, performance-based cleanup site. There was approximately 1,000-gallon discharge of gasoline in March of 2007. Shortly after that, they did a source removal by excavation, and then a series of consultants and technologies worked on the site, and they've done groundwater treatment by pump and treat, by bioremediation, and by injection of hydrogen peroxide. They were none ultimately successful. There were varying degrees of success, but there was still a fair amount of residual contamination out there. Of even more concern was there was off-site migration of toluene, ethylbenzene, and xylenes, naphthalenes, and total recoverable petroleum hydrocarbons. The site layout is, this is the Reef Deli site. It was a gas station, now a convenience store. You can see the dotted outline was where the tanks had been and what was excavated. And then the contamination went across Front Beach Road. This was a former hotel site that's been raised, and actually went, there's a sea oats area here, and then all the way out onto Panama City Beach at one point in time. There's a close-up of October 2017 concentrations of total xylenes. You can see in better detail the excavation area here. Note that excavation stopped because of this overhead power line. They couldn't get too close to that. Obviously, Front Beach Road is pretty heavily traveled road, and they could not excavate or do anything out in the roadway itself. So residual contamination, as would be expected on the south side of the excavation area, a lot of mass underneath Front Beach Road where we really couldn't access it. And the highest concentrations in any monitor well were actually in this off-site well, monitor well 8. So, you know, lots of concern about how we were going to address this. Let's see. And here's a aerial photograph view. The red showing the same concentration outline with the Reef Deli site up here, and this was the former hotel site with the sea oats area and the beach itself. So not awful working conditions. For some reason, I don't have any real problem in getting volunteers to come work on the site. And REGENESIS actually had some guys come from California out here for some reason. I don't know. But you know, you got to worry about the sun and the sand and that kind of stuff getting in all your equipment. Let's see here. Of more interest to this presentation, this is monitor well 8, the little black dot there. The concrete cutouts had been involved with a former system. And a somewhat complicating factor when we first started this, there was no utilities in the general area. Now you'll notice these yellow lines here. The city had come in and put in a natural gas underground line there, so we had to stay off of that, which kind of knocked our original plan to do a grid pattern all the way around the well and the head. So not a huge complication, but something to be aware of, and certainly an object lesson in why you always do your underground utility locates before you start doing any kind of digging or injections. The other thing to note is because this was a raised hotel, there's nothing but a foundation left. There's no water on the site. The closest fire hydrant is across Front Beach Road, kind of right by that little tree you can see there. So one of the things we had to do was actually bring in a truck with a water tank, and we were ferrying water across Front Beach Road from the fire hydrant to use. Historically, concentrations have been up and down. I'm sure the guys that had the site in 2015 thought they were closing in on cleanup, but you know, this is from 2013, so 6 years after the initial release. You had 40,000 total contaminants. It dropped down and then bounced back up and then bounced back down. But you can see when we were looking at it in 2017, it was still around 20 ppm, 20,000 micrograms per liter of total contaminants. Benzene was gone, which is good news, but toluene, ethylbenzene, xylenes, naphthalene, and total recoverable petroleum hydrocarbons were all of concern. The groundwater cleanup target levels that we're being held to are shown there also in micrograms per liter. Well, we put together a pilot test plan in consultation with REGENESIS. We focused on monitor well 8 as the off-site well, which obviously was a concern. We'd like to bring everything back to the site, and also the hottest well. The plan called for 1,700 pounds of PetroFix, including 40 pounds of an electron acceptor salts in an aqueous dilution. This, as I said, was the first field application. So they're taking it out of the lab into the field. And one of the things they were looking at is what dilution could be injected the most effectively. So they were playing with dilution rates. They did a lot of pre-injection and post-injection borings to look at the lithology and the distribution of the PetroFix after it was injected. But the plan called for injection from 10 feet below land surface to 20 feet below land surface, with the groundwater table at about 10.5 to 11 feet, so just slightly above the water table to basically 10 feet below it on 7-foot centers. We used, as I said, FlumeStop is sort of a sister technology to this. DEP requires an innovative technology acceptance letter, which is a letter that says, we've looked at the technology, we don't think it's going to cause any problems, and here are the underground injection control parameters you need to monitor for during the test. So we used that, worked with the district office over there in Pensacola, who were tremendously helpful, and got our plan approved. As I said, the cleanup goals are the groundwater cleanup target levels in Chapter 62-777 of Florida Administrative Code. For those of you that aren't in Florida, that'll make perfect sense to those of us that are based in Florida. To those of you that aren't, as opposed to doing a risk assessment site-specific, what Florida did was come at it from the other direction and had a group of risk assessment and toxicological professionals come up with a table of cleanup standards. The groundwater cleanup standards are basically the federal maximum contaminant levels, the MCLs, the primary drinking water standards, and then they set standards for a number of other compounds based on that level of health risk. And this went through a full rule development workshop, public noticing, acceptance, and all that. This wasn't just something thrown out there by DEP, but it gives you a tabularized list for several hundred compounds that you can simply look up the cleanup standards. Associated with this, there's also what they call a natural attenuation default concentration, which based on the health risk is either 10 or 100 times the groundwater cleanup target level, that we frequently use to determine whether to go to active remediation or look at natural attenuation, that kind of thing. So if you're interested, you can look that Florida Administrative Code reference up for all those cleanup target levels. The pilot test was approved by DEP at the end of February 2018, and we implemented it almost exactly a month later in March of 2018. As I said, we didn't have water on site, so we were ferrying water over to this poly tank here. And then we had the PetroFix on the back of the truck, on the back of the drilling truck there. This is REGENESIS's mixing trailer. So they've got mixing tanks in there. We would take the PetroFix, they were bringing it in 5-gallon buckets. You can see that black. It's a very, very black, if you've ever seen granular activated carbon, same stuff that you use in aquarium filters and that kind of stuff. It's pitch black, and this is a pitch black liquid. They were putting it in there. They have a bunch of pumps and metering devices in there, and then it was coming out with this hose, going through some more meters and pressure gauges out here, and then getting injected through a direct push technology drill rig. That's monitor well 8 that we saw previously. You can see each one of these little white dots was a DPT injection point or boring. That's not to say that every one of these we had PetroFix injected in. Like I said, a lot of what we were doing was going slow and taking pre-injection lithology borings, and then post-injection looking at how the PetroFix had distributed in the subsurface and comparing that to the various dilutions. Here's one of those cores. One of the reasons that REGENESIS was interested in this site was this is probably as close to a laboratory sand tank as you're going to find in nature. This is all beach sand. It's a very fine-grained sand. You can see, white, and then it gets into some staining from the petroleum. But that's what we were injecting in. So injections were relatively low pressure. Generally, most of them were less than 30 psi, and we were getting pretty high flow rates. I think we got upwards of 10 gallons a minute in a couple of those holes. So, yeah, ideal injection scenario. And here's some of the results. You can see here, this is a silty kind of clay sand layer that pops up at about 21 to 25 feet below land surface. And then you can almost not see this because it's so black, but that is the core from 10 to 15 feet where we were doing the injections and obviously trying to focus right there below the water table. And you can see it's a uniform black. We got great distribution in the subsurface there. And that's one of the nice things about PetroFix is you get a real visual indication of what's going on. There's no special equipment required to begin to see whether you got distribution or not. If it's pitch black, you got it out there. Now, PetroFix works through a two-part mechanism. The first is obviously just direct absorption onto the carbon, similar to any granular activated carbon vessel. Exactly same mechanism. Once it's in the environment and has plated out on the soil particles, it also provides a really ideal substrate for biological degradation. And as the degradation continues, the bacteria eat the contaminants, they basically free up a sorption site. And then another molecule of contaminant can get attached to the carbon, and then the bugs can eat that. And it's a repetitive, almost in situ renewal type process. With an expected life of this, based on a lot of laboratory testing that REGENESIS has done, of years to possibly decades. So this opens up, in terms of what we are doing on this particular site and any other site, the option, it's not just injected and cover the entire source, but you can also begin to think of this in terms of permeable reactive barriers, where you're putting in lines and simply letting the groundwater come to you and treating it as opposed to doing a complete grid over an entire area. So again, basically an in situ carbon vessel, if you want to think of it that way, where you're doing the injection, and that's really the goal, is to get really good coverage over your area of interest. So did it work? I think the answer is pretty conclusively yes. You saw the first some of this data earlier. This is 2016 and 2017. You're in the thousands here. We injected in March, the end of March. So May was the 60-day post-injection test. The U means it's undetected at that particular method detection limit. Everything's undetected at 90 days or 1/4 post-injection, undetected. 180 days, undetected. We're now, we've got a couple of little blips that showed up actually below the reporting limit, but in essence, for a solid year since we've done the injection, everything is BDL. Not just below the cleanup target levels, but below laboratory detection limits. I've not seen anything like that in 37 years. And I was around for when air sparging and soil vapor extraction were the newest, greatest things. I think it's in line with that as far as a disruptive technology. Now, obviously, it needs to get proved in the field, and we're working on that. But that's just incredible. Really happy with those results. So our conclusions were, we got below detection in 60 days. It stayed there for a year. We didn't know that at the time, but it has. The total cost for that pilot test was about $50,000. Now that was elevated, as I said, due to the multiple borings we did and the extra days we spent on site. But even that is not an enormous amount of money compared to what we normally spend on remediation. The obvious conclusion was, let's get the full-scale design as soon as we can, and DEP agreed and approved the pilot test in August of 2018. So we proceeded to the full-scale design, submitted the remedial action plan in early October 2018. Now, as an engineer, one of the really interesting things to me and attractive things, in addition to the performance, is the fact that there's a self-design internet application, petrofixcom. You go in, you enter in your site characteristics. It gives you a recommended spacing and dosage along with pricing. So you can do that all online at your desk. Now, obviously, Todd and the REGENESIS team are available to help you if you've got questions or just want to go over it with them. But compared to every other technology out there where it's all proprietary and you're relying on somebody else to do it, that's a huge benefit to me. The area that's left on the Reef Deli site itself, so north of Front Beach Road, is about 1,600 square feet and is 2 wells, Monitor Well 2 and Monitor Well 7R. Water table there is around 13 feet, so our zone of influence that we wanted vertically was 13 to 23 feet. The application called for 2,800 pounds of PetroFix in 11,000, almost 12,000 gallons of water and 44 injection points, which was a 6-foot grid pattern. Estimated cost for PetroFix and DPT injections was $35,000. Now, this was the plume in June of 2018, which is what we were using to base the design on. Monitor Well 8 had cleaned up. So we were left with the outer ring is the groundwater cleanup target levels, or the MCLs in primary drinking water contour. The inner is the natural attenuation default concentrations. And those are your 2 wells, Monitor Well 24 and Monitor Well 7R. We had good up gradient control with the clean well, good side gradient control with the clean well, and Monitor Well 3 had been cleaned for some years at the time it was abandoned. So we're pretty confident that the groundwater plume is on the southern side of this site and obviously extends underneath Front Beach Road. But because of the pilot test work we did around Monitor Well 8, not only is Monitor Well 8 clean, but essentially we've got a permeable reactive barrier here addressing that mass that is coming out under Front Beach Road. And there was the grid pattern. We just tweaked it a little bit to kind of work around some of the site features, and obviously we're going to push it as close to the road as we can get that DOT will allow us, but we're not allowed into the road. So, are we going to talk about the full-scale successful implementation of this? Well, as the immortal words of Lee Corso, not so fast, my friend. Not so fast. We had a couple of hiccups in terms of some regulatory hoops we had to jump through. We had, just like the pilot test, going in under FlumeStop's Innovative Technology Acceptance Letter, because again, it's sister technologies, and I reasoned that if it'll work for FlumeStop, it ought to work for PetroFix. DEP disagreed with that interpretation. They reviewed the initial submittal, came back in early November and said, hey, looks great, but you have to have an innovative technology acceptance letter specifically before PetroFix, before we'll approve this. It got really complicated because the guy that had done it for the previous 10 years or so had retired that summer. So REGENESIS had verbal contact with the new person starting in early fall. They did their initial submittal in November of 2018. Lots of back and forth and discussions. And we kind of got to an approval in May, which we thought was really good results. Now, because the UIC parameters changed slightly, we had to do an addendum to the original full-scale design that we had submitted. We got that in a couple of weeks after getting that acceptance letter. And they came back about a month later and said, hey, great, you're all approved, except because the zone of discharge extends off-site, rules require us that you notify all the off-site property owners via certified letter and public comment period that it's going to extend off-site. So that's been done. We expect everything to be wrapped up and approved by the end of this month. And that will then allow us, once I can get the driller schedule, to actually go to full scale in December or possibly January. So we're there. I'm a little frustrated that we haven't gotten this site already done and closed out, but so far so good. The results are tremendous. So that wraps up. I think we're going to hold all questions till the end. So I'm going to turn that. Here's just for proof. Here is the Innovative Technology Acceptance Letter for PetroFix. You can get that either from Todd and the REGENESIS team, or you can get it off the DEP's website if you need it. And I'm going to turn this over to Chad Northington.
All right, well, thanks, Gordon, and really appreciate everyone joining us and participating today for this discussion. So I'm going to go a little bit deeper into the formulation of PetroFix, and I'd also like to kind of distinguish between FlumeStop and PetroFix. I know that's a question that's come up quite a bit and that Gordon alluded to. So I really like to begin with this figure here. Sorry, let me get my direction. So we like to call this the 4 pillars of in situ remediation. So when you're thinking about choosing a technology or a strategy in the in situ world, you really want to be thinking about these 4 things. And I would say as an industry, we've really gotten the reactivity or the chemical and biological reactions right, the ease of use, the equipment that we use, the mixing component above ground. We've figured that out pretty well at this point. But as an industry, in terms of distribution in the subsurface and the persistence or the longevity of in situ reagents, that's been a bit of a stumbling block in general. And so when you're thinking about these things, colloidal reagents really have created an opportunity, and really is the next step, I think, in the evolution of the in situ remediation world. So I want to take a look at how we developed this particular technology and where it started. So as Gordon alluded to, this really kind of stemmed from the development of FlumeStop, which launched in 2013 after many years of R&D work. It's been applied nationally and internationally at over 500 sites worldwide, and really has been recognized as a leading technology in the in situ world for both the treatment of chlorinated solvents, hydrocarbons, of course, and now we are using it for passive plume management and treatment of per and polyfluoroalkyl substances, or PFAS. You can see that natural evolution. We wanted to improve upon that. Sorry, guys. And we looked at FlumeStop and said, well, how can we make this better for hydrocarbon, petroleum hydrocarbon cleanup? And essentially, there were several areas that we focused on. First of all, we wanted to look at higher mass sites. With FlumeStop, there were some limitations in terms of mass concentrations that we could handle. And so we wanted to improve in that area. Gordon and I have worked on a previous site where we actually did a mass reduction step first and did that with chemical oxidation so that we could transition to FlumeStop. In the case of PetroFix, we can often eliminate that first step, that extra phase, so to speak, and move directly into PetroFix remediation. So the other thing is we often would co-inject an electron acceptor with FlumeStop. In the case of PetroFix, it's already built in. We can mix it above ground. Part of it's built into the formulation. I'll show that to you later. And we can move right into injecting all that as a single material rather than co-injecting electron acceptors. And also, as Gordon alluded to, we have turned this into a take control sort of process. So as an engineer, Gordon alluded to the fact that he likes to be able to have the design in hand, be able to work through the numbers, but not just the design, but also the application of this material. So from start to finish, the user's able to move through the design and application process. And it's a very cost-effective technology for multiple reasons. As I mentioned, we can eliminate sometimes an additional mass reduction step. Being able to self-apply has some built-in cost efficiencies to it. And I think that probably by getting the electron acceptor built in, we've certainly allowed for a more efficient process and cost effectiveness. So I want to take a look at activated carbon just in general and kind of compare that to colloidal carbon. So we're all familiar with granular activated carbon, or GAC. That's on the scale of about 400 to 1,000 microns. That might sound small, but it's really not, and I'll show you why. And of course, if you're going to apply this in the subsurface, you would need tremendous pressure. You're going to cause fracturing or fracking of the subsurface. And it's a similar situation even if you go to a powdered activated carbon. Although it's 50 to 250 microns, you're still going to need high pressure. You're going to get kind of a random distribution of that material and cause fracturing in the subsurface. However, with colloidal carbon, it's 1 to 2 microns. And so what you're able to do is actually move that material through the pore throat diameters of a typical geology and not result in this fracking. We can inject at pressures generally less than 50 psi. On the Reef Deli site, we're able to inject at about 30 or so or less. And then that's obviously not going to result in a fracking scenario. We actually prefer flooding to fracking is one way to think about it. So we're trying to distribute this material across what we would call the flux transport zone. So this is where the contaminant is moving. It dictates the architecture and the plume behavior. And so that's what we're trying to get to, that target treatment zone, and try to distribute across that entire zone rather than fracking this material under high pressure. So in terms of the modes of action, I'm going to give you a visual here. So Gordon had alluded to this. I want to do it visually. So the first step here is you can see that there's injection of material. It's going to create kind of a light coating. It's going to become a part of the aquifer matrix. I like to say it actually paints the remedial landscape. So we're converting the subsurface into a carbon filter essentially. And we're not blocking the pore throats. We're not changing the hydraulics of the system. We're creating a carbon filter in situ. And then after that happens, you can see that the microbial community now moves in. They start to build some of their microbial condos, and they're going to occupy essentially this large surface area that's provided by the activated carbon. And once that starts happening, you'll see that they start to degrade and munch on these molecules and essentially free up new sorption sites by naturally in situ regenerating that carbon surface. So as long as these microbes are receiving what they need, they reach a state of what I would call biological or biogeochemical bliss is what I like to refer to it as. So that's the general process. That's going to apply both to PetroFix or FlumeStop. It's colloidal in nature, and they both behave in the subsurface that way. But let's look at a couple of the differences between these two colloidal carbons. So first of all, one major aspect or difference is the amount of carbon in the reagent itself. So FlumeStop is around 4% or more as shipped, whereas PetroFix is going to be in the 7 to 8 times more carbon content range, over 30% generally. So you're getting a lot more carbon and a lot more sorption capacity built into that. So that's one of the reasons that we're able to use it for higher mass sites. Now, FlumeStop has a very unique dispersion chemistry. It has a natural organic polymer built into it. It's what allows it to distribute, but not indefinitely. And then that polymer essentially degrades and it bonds to the aquifer matrix. PetroFix doesn't have that same chemistry. And you can think of it as kind of the price to pay a little bit for adding in the extra carbon. So you're going to have to do a little tighter spacing, generally maybe in the 5 to 6.5, 6.5 foot range where you're on center. So that's another difference between the two reagents. FlumeStop generally is used as a platform, and then we're co-injecting different reagents with it to determine how we want to handle the particular contaminants of concern. Whereas PetroFix was really formulated specifically to deal with petroleum hydrocarbons with that built-in electron acceptor. And then FlumeStop is something that REGENESIS does the design for. We apply it with our services division, REGENESIS Remediation Services, RRS. And PetroFix, however, is something that the user can take and run with from start to finish. So those are some of the distinguishing features between them. So let me dig in a little bit more on the PetroFix technology and some of the key features. So again, this is a micron scale activated carbon, and sometimes I have a hard time putting my head around what does 1 to 2 microns mean. Well, think of it as the size of a red blood cell or size of a bacterium. So we're talking really, really small stuff here. It's hard to think of it as a particle in that sense. And then we're using an anaerobic pathway via nitrate and sulfate electron acceptors. Another thing I'll talk about in a little more detail here. And of course, it treats a very broad spectrum of petroleum hydrocarbons. Of course, your BTEC suite, you saw some of the numbers with the TPH on this particular site we're talking about today. And we can use just standard equipment to apply this material at low pressures and high volume and very wide area distribution. With standard tooling, standard injection materials, and whether we do that with direct push or injection wells. And also, as Gordon mentioned, generally up to free phase is kind of fair game for PetroFix. So let's look at this a little closer. So we know we got micron scale carbon. We're shipping this at generally above 30% carbon. And again, it actually has sulfate built in the form of calcium sulfate dihydrate. That's actually built into the materials it's coming. And then you get this drum along with a bucket of electron acceptor. With this electron acceptor, you have two choices. You can do the 20-pound blend of sulfate plus nitrate, or you can do a sulfate only or a nitrate-free version. And that's really, generally we recommend the sulfate and the nitrate version, the combined. It's going to be more efficient. But if there's any sort of concern on the part of a regulatory body, for example, there is the option to not have the nitrate. I have not seen that as a problem. Generally, everyone has accepted the sulfate nitrate blend, which is, again, preferred in this case. So I'm not going to dig too deep into this, and this may be a new term for some folks, but what we're doing through this sulfate nitrate pathway, this anaerobic pathway, is promoting a process called syntrophic bioremediation. And essentially, syntrophic bioremediation is referring to a community of microbes eating together and using the same, simultaneously using the same carbon source and the byproducts in that process. And what it does is it contributes a synergy and an efficiency to the degradation of these petroleum hydrocarbons. For me, kind of the best analogy with Thanksgiving coming up, you know, our side of the family, we love to do the turkey, the hams, the mashed potatoes, kind of the traditional stuff. And then my wife's side of the family, we have a Lebanese component. So we get to do mesha, some grape leaf stuff, some tabbouleh salad, and all of that. What it results in is a more efficient eating. So the more we can bring to the table, the better off we're all going to be. And I think it's a similar analogy on a much different level here with the syntrophic bioremediation. But what's interesting is once those electron acceptors are potentially depleted, the byproducts, essentially the hydrogen, the acetate, can be used by methanogenic communities to continue that process. So this keeps going maybe after these other electron acceptors are already used. So if you guys want to dig into this a little bit deeper, we have a great technical bulletin on the petrofixcom website, and it goes into a lot more detail into that process. So let's look at some of the different applications. You already got a taste of that with Gordon's presentation. You know, just generally in terms of how this material is applied, it's very easy to work with. You can see it can be very simply pumped or poured into the larger mixed tanks, and it takes very little agitation to get this mixed into a larger batch volume. So just a little gentle agitation, and this stuff almost magically goes into a larger solution. So very simple to work with. And Again, here's some examples of that nice tracer characteristic of PetroFix. So you can see not just in the soil cores, that's very obvious there in the pictures to the right, before and after injection, but even in the monitoring wells. You will see influence when you're injecting around a monitoring well. You can see that show up in the well, and that's a great thing. That says we've got that material to move through that flux transport zone to come into the monitoring well, and we can see that. If you want to remove that quickly, there is a flushing procedure that you'll see instructions for on the website. However, that material will subside in a relatively short period of time and bond to the aquifer matrix. So here's kind of the version where we're going right now with the Fullscale at this site with the grid treatment and addressing both the smear zone and the saturated zone. That's a very common application. And then we've already kind of done this at MW8, where we have a permeable reactive barrier of sorts, and not just stopping and absorbing that material, but it's being degraded in place at that barrier. So you have this clean waterfront coming out the other side of the barrier, essentially. And then there's a third scenario. Historically, folks have used our ORC advanced pellets in excavation scenarios, and that's a great means of promoting aerobic bowel remediation. But now with PetroFix, we're able to actually do kind of a 1-2 punch. So we also are adding in electron acceptors with it, so you still get that component of the bio, but we're also adding a long-term sorption component that's going to continue to work long after maybe the electron acceptors have depleted that we've initially added. So this is going to be just simply spray applied into the excavation, and it can even be used to prevent, so to speak, continued future pollution if there were maybe a spill that occurred in that zone. So this is a very effective way when you have the pit open to provide both a long-term and a short-term means of dealing with that residual mass. I would also add that you could add ORC advanced pellets with this to provide a very robust electron acceptor chain going right through that redox potential chain, and add that as well into this mix. So again, just to reiterate, petrofix.com, if you go there, you'll find a multitude of resources, including the design assistant, SDSs, technical bulletins, everything you would need to create your plan, work plan, or design is available on that website dedicated to this particular technology. So let's look at just some of the recaps here. So first, we have a very broadly applicable technology across numerous types of applications, from source area to barriers. Very safe and easy to apply. This is not going to be incompatible with infrastructure in the subsurface. There's no problems with injecting it around active utilities or tanks. And again, this is colloidal carbon, so you're not dealing with things for larger particle carbon like carbon dust that might happen. And then we're adding this at very low pressures, high volumes with standard equipment, and getting very good distribution in that flux transport zone. You only need common equipment to apply this, either through direct push or injection wells. And you're going to find this tracer quality makes it very easy to make sure you're getting this material where it needs to be. And all these online resources are available to everyone. But again, we are certainly still here to assist with that, whether you want to contact Todd or myself. We can provide any sort of support you need from the design to the application, and are here to continue to support you in that way. So with that, I will hand it back over to Dane and your questions. Thank you.
All right, thank you very much, Chad. That does conclude the formal section of our presentation. So at this point, we would like to shift into the question and answer portion of the webcast. Before we do this, just a few reminders. First, you're going to receive a follow-up email with a brief survey. We really do appreciate your feedback, so please take a minute to let us know how we did. And also, after the webinar, you will receive a link to the recording as soon as it is available. All right, so let's circle back to the questions here. Got quite a few questions here today. It looks like a lot of them are going to be for you, Todd. And let's see, here's there's a couple with regard to distribution. So there's one question saying, has PetroFix been successfully applied in lower conductivity materials? And then there's another question that asks, how well will PetroFix distribute into silt, clay, etc.?
Thank you. Yeah, thank you, Dane. Thank you, Chad and Gordon as well. Great presentations there. The answer to that is yes. I want to refer back to, if people can remember, there was a slide that Chad showed that the not only referred to the size of PetroFix as the size of a red blood cell, but also showed the average pore throat size of fine sands down to silts, and silts being commonly in the 3 to 8 micrometer pore throat diameter range. So just from a physical standpoint, the material itself can fit and flow under low pressure into low permeable soils. So to answer that is yes. Now, what we try to do to effectively do this is that we are trying to put PetroFix into what we call high conductive zones. It's the zones or the highways where contaminants are going. We are not trying to put PetroFix into a tight clay. We recognize that there may be contamination in that tight clay, but more so what we're trying to do is get I like to use the word almost like a spray paint coating of PetroFix around all the tight zones. And oftentimes it does go and diffuse into those tight zones a certain amount. And we can do that with the small particle size of PetroFix. And importantly, by using tooling that we call, or is called in the industry, multi-port tooling, instead of using thin, single row, high pressure tooling to inject or possibly even propagate a fracture, if you inject this suspension using tooling that injects over 2, 3, or 4 feet of vertical aquifer simultaneously, you'll find that this material floods into even what people would consider tight zones. Like I live here in Colorado, there's a lot of glacial till. We have bedrock down about 22, 24 feet. We have weathered bedrock above that. There's a lot of skepticism about doing this, but with the right tools, on the right techniques, we can actually get PetroFix fully flooded into that formation using pressures often below 60 psi. One important thing to note about that is we don't like to take that for granted, and we have tried, and I'm trying to continue to educate the market on how to do this successfully. And so I would like to direct the audience attention, if you want to know more about this, to some PetroFix application instructions that can be found at petrofixcom/resources, and it goes into much greater detail on applying in tighter soils and how to document distribution of the material.
Okay, great. Thank you very much,
Yep.
Todd. Okay, so we have a question for Gordon. This is about the case study presented, and the question is, were there any problems with daylighting of the PetroFix?
No, we did not have any problem at all. Groundwater was at 10 to 11 feet. And like I said, we were injecting mostly at about 20 psi. Occasionally we had to pump it up to close to 30, but we were getting anywhere from 1 to 3+ gallons a minute going into there. So really easy injection, no issues at all with daylighting.
Okay, great. Thank you so much, Gordon. So this is a question for Chad. And Chad, the question is there any concern with injecting into or near a drinking water resource? And this, the person asking this question goes on to explain their specific site, that they have a spill site on the edge of a reservoir, but their remedial options have been limited due to regulator concerns with injecting.
Yeah, that's a great question. No, there shouldn't be a concern. I'll start with that. We have the ability to, what we like to say, park the reagent. We have a parking reagent that can prevent any further migration or provide a sort of insurance to stop migration if that's a concern. So that's one aspect of it. And so that can be controlled. And again, the distribution and migration of PetroFix is very limited. Relatively speaking, again, we're generally seeing, 5, 6.5 feet of spacing. So you shouldn't expect that to migrate very far. So it can be controlled both in terms of how we can manage it in situ, but also just the nature of the reagent itself doesn't lend itself to long migration paths.
Great. Thanks so much, Chad. Let's see, here's another question for you, Todd. And it is there a concern for spent carbon within the injection area?
That's a great question. I think that probably alludes a little bit to Gordon describing this as kind of a container, which I think also is a good analogy. So there is a finite sorption capacity of carbon. So yes, theoretically, yes, it is possible to say I have a spent or a fully sorbed carbon source. What we try to do in our designs, however, is we do try to provide enough PetroFix carbon to fully sorb all the groundwater contamination and a significant amount of potentially desorbing soil contamination on top of that. So, but more importantly, and also referring to, as Chad discussed this, there is a regeneration component intentionally built in. So by adding nitrate and sulfate, and actually also promoting syntropic biodegradation, we are essentially regenerating the carbon in situ. So we're not just relying on sorption. This is a sorption plus bio approach. And we have found that combination together helps avoid a sort of a spent carbon scenario where it's continually regenerated in situ. And you can see that most prominently as we go through time, sites like Gordon's site, that he's at non-detect, continually at this site, and showing that in that case, no, we haven't spent it. But yeah, hopefully that answers that question.
Okay, great. Thank you so much, Todd. Here's another question for Gordon about the site, and it is, what geoprobe tooling was used downhole to perform the injection, and what type of pump was needed to inject?
It was standard DPT geoprobe tooling for injections. I don't know exactly what they used, but there was nothing special that. I believe they got some Moino pumps in the injection trailer that they were using. It was either Moino, I don't think it was double diaphragm. Pretty sure it was Moino pumps. It wasn't our trailer, it was Regenesis's trailer, so I can't definitively answer that. But again, pressures of less than 30 PSI and less than 5 gallons a minute flow.
Okay. All right, so here's a question, another question for Chad. And Chad, the question is, with regard to carbon sorption sites, is there a concern about bacterial growth and or other organic degradation products blocking these sites for resorption by more hydrocarbons?
So no, we haven't witnessed any sort of changes in the hydraulic parameters at sites where we're looking long-term monitoring or even re-injecting. So, some folks have asked, say, about biofouling in the subsurface or something of that nature. Again, this is happening on the surface of the aquifer matrix. It's on a micron scale, and there's not a buildup that we're seeing. We've done that in the lab, we've done it in the field, but see no evidence of any sort of significant change in the hydrogeological characteristics of the subsurface where we've injected.
Okay. Let's see. Todd, here's a question for you. It is, will this technology work on more persistent methylated benzenes?
Like trimethylbenzene?
Yeah, the person lists here 1,2,4 trimethylbenzene.
Yes. So I guess my answer to that is, TMB is slowly a slow degrader for chemical. In fact, 20 years ago it was, or has been used as a recalcitrant tracer. But there is evidence that it does degrade slowly with, interestingly, nitrate and iron together. I guess one could argue that might be a co-metabolic approach, but I would say as much as anybody could expect it under normal enhanced conditions, which there is evidence for that, I would say yes. TMBs will definitely sorb strongly to PetroFix and be held in place while this occurs. But we don't actually have any direct evidence right now, any ground results or a site to actually document that at this time.
Okay, thanks, Todd. Let's see, here's another question for you. Todd, and it is, have you ever experienced an ISCO site where persulphate was injected after PetroFix or FlumeStop, and the ISCO chemicals were sorbed to the carbon matrix, preventing petroleum oxidation?
It's a good question, because I do think it is reversed that way. We do, I guess to answer that is no, I'm not aware of a site that somebody has come back and done that post PetroFix application. We would hope that it would be the reverse, that PetroFix sort of saves the day, post ISCO application. So another point on that I want to make is that there are some oxidants that users should be cautious about injecting around PetroFix, or for that matter, FlumeStop, and that would be persulphate-based oxidants. The carbon, we have done research, can accelerate that reaction quite a bit. And so, I just ask the audience to be cautious if they've done a PetroFix application and they want to do say a persulfox going into the ground, just to be aware of that. So other products that REGENESIS has, like sodium percarbonate-based REGENOX, we don't think is going to be as big of an issue.
All right, thanks, Todd. Chad, this is a two-part question for you regarding North Carolina. Has PetroFix been used in North Carolina? That's part one. And then part two, is PetroFix pre-approved without 5I permitting in North Carolina?
I might pass this one back over to Todd. He's been working diligently on that, so I'll let him go ahead and speak to this status of approvals there.
Yeah, so we actually, we do have approval through the UIC program, but as far as the, I'll probably get the program wrong, but as far as the insurance UST reimbursement program, it's still being reviewed for pre-approval at this point. So I would imagine if somebody has a project going through that side of the program, it may take a couple months to get through. I'm hoping by then that will be the case. We actually did indeed just ship PetroFix for our first site in the state, in North Carolina. I think it was last week.
Okay, great. Let's see, here's another question for you, Todd, and it's, has it been used in any cold climate locations?
So yes, PetroFix, well, has been used at a number of sites in Canada. We have a site that was just injected in Alaska. So yes, we have. As far as temperature is not going to affect anything related to the carbon itself. It's not going to affect the ability for it to be injected in the sorb, other than the material obviously is largely water-based, as it comes in a water suspension. If that water freezes, obviously you're going to have to thaw it, and the material actually can be thawed if that happens, and rehomogenize and just mix and inject, and that's not going to be a problem. I guess the big assumption might be, what does it do for kinetics of biodegradation? It's been my experience that even getting down to ranges close to freezing, or in groundwater low degree Celsius ranges, you still do have measurable rates of anaerobic biodegradation. And so it may take longer, but in the case of PetroFix, that's okay, because what you've done is you've pulled out all the contaminants and you've essentially parked them on the PetroFix, where they can be in proximity to bacterial, or I guess the microbiology of that particular environment, and whatever rates they're degrading, that PetroFix is not going to release that material. So I think that will help overcome any suppression of rates due to temperature.
All right, thank you very much, Todd. Gordon, here's a question for you about the site, and it is in the pilot test well, has it been sampled for the UIC parameters since injection?
Yes, it has. I do not believe there were any exceedances. I'd have to go back and verify that. But yes, we did both a baseline to establish natural conditions as well as quarterly sampling.
Okay. All right, and here's a question for Chad. And the question is this the case study presented by Gordon, is this the only application of PetroFix in Florida? And they say that Florida Department of Environmental Protection often wants 2 or 3 successful applications to approve. So yeah.
So yeah, in terms of in the ground applications, yes, but that is partly due to the process of getting the approval, the UIC approval that Gordon alluded to. So there's a whole bunch of stuff coming down the pipe going into the end of this year into Q1 now that the floodgates have sort of opened and we can move forward with approval. So buckle up, everybody.
Yeah, I think we've got
Fact.
3 that are scheduled before the end of the year. So we were just waiting on that technology acceptance letter from DEP.
Okay, great. And with that, that's going to be the end of our chat questions. So thank you very much, Gordon, Chad, and Todd. If we did not get your question, someone will make an effort to follow up with you. If you'd like more information about environmental services from Advanced Environmental Technologies, please visit aetllc.com. And if you'd like more information about remediation solutions from REGENESIS, please visit regenesis.com. Thanks again very much to Gordon Dean, Chad Northington, and Todd Herrington. And thanks to everyone who could join us. Have a great day.